Hello and welcome to this lesson on standing waves, which is part of the waves topic in AQA A-Level Physics. So in this lesson we're going to look at explaining the properties of standing waves. So if we've been successful and we've learnt in today's lesson, we should be able to explain what is meant by a stationary wave, define the terms node and antinode, then describe the formation of a stationary wave by two waves of the same frequency travelling in opposite directions, which is in the following part of the AQA A-Level Physics specification 3.3.1.3, principle of superposition of waves and the formation of standing waves. So a progressive wave is a transfer of energy due to the oscillation of particles or fields. So a progressive wave carries energy from one place to another without transferring any material, and a progressive wave consists of oscillations passing through a medium or a field carrying energy with it. So a progressive wave transfers energy away from a source, so the source of that wave loses energy. But there is another type of wave, a stationary wave. Now a stationary or standing wave is the superposition of two progressive waves. So two progressive waves must be coherent with each other, so they've got to have the same frequency, amplitude and wavelength. Now the two progressive waves, to produce a standing wave, must be moving in opposite directions with each other, and unlike progressive waves, no energy is transmitted by a stationary wave, rather it's a display of energy. Now superposition happens when two or more waves pass through each other. As they are vectors, they'll add when they overlap. Now superposition is an example of interference. Now interference is a property of all waves. So in superpositions, beforehand the progressive waves head towards each other. At the instant the waves cross, the displacements due to each wave combine, and afterwards each wave continues on its own way. Now the principle of superposition is that when two or more waves overlap, the resultant displacement equals the vector sum of the individual displacements. Now only coherent progressive waves can interfere, and coherence is obtained when the waves have a constant phase difference and have the same frequency. Now the superposition of waves can result in interference. So when two waves meet, if their displacements are in the same direction, the displacements combine to give a bigger displacement. So a crest plus a crest gives a bigger crest, and a trough plus a trough gives a bigger trough. So we call this constructive interference. Now points on waves which constructively interfere have a phase difference of 2 pi radians or any multiple of that. So we say that they are in phase. Or we could also say that points on waves which constructively interfere have a path difference of lambda. Okay, they are in phase. So if a progressive wave meets with a positive displacement meets a wave with a negative displacement, then they will cancel out. So it's important to note that the displacement of the combined wave is found by adding the displacements of the two waves. Now this is called destructive interference. Now if two waves with equal and opposite displacements meet, so for example a crest and a trough with equal magnitudes meet, they will cancel each other out completely. Now we call this total destructive interference. Now points on the wave which totally destructively interfere have a phase difference of n pi radians. So pi radians are any multiple of that, and they are completely out of phase. So they have a path difference of half lambda, so they're completely out of phase. Now a stationary wave can be produced on a string by setting up a driving oscillator at one end of a stretched string with the other end fixed, as shown in the diagram below. So a wave is produced by the oscillator and sent down the string. What happens is that the wave is reflected off the fixed point and moves back in the opposite direction. So you've now got two progressive waves. So the two waves will interfere with each other and produce a stationary wave. Now the two waves will interfere as they are coherent with each other and they overlap with each other. So the two waves interfere and produce a stationary wave as shown in the diagram and animation below. You can see it more clearly in the following animation, which shows you the idea of both of the waves working through. Now, it's also important to note that your standing wave will overall will look something like the following animation below. Now, for most frequencies, the resultant pattern will be a jumble. However, if the oscillator happens to produce an exact number of waves in the time it takes for a wave to get to the end and back again, then the two waves reinforce each other. Now, the frequencies at which this happens and produce the following pattern are called resonant frequencies. They cause the stationary waves where the overall pattern stays constant. The string just vibrates up and down, making loops as shown in this particular diagram. So the following is an example of a stationary wave in water, and the following is an example of a stationary wave on a string. So you'll see loops vibrating because the points of vibration stay constant in your stationary wave. Now, it's important to note that you will get the following pattern in a stationary wave at a resonant frequency. Now, note, by the way, this is a transverse wave, so the particles vibrate at right angles to the string. Now, you'll notice that there are two types of labels on these diagrams. Nodes are points on the standing wave where the amplitude of vibration is zero. The particles do not move. Now, it's important to know that at nodes, the particles present have no energy. Now, nodes are half a wavelength apart on a standing wave. Now, nodes are caused by the total destructive interference between the two waves produced in the two progressive waves that produce your standing wave. Now, antinodes are points on the standing wave where the amplitudes of vibration are a maximum, which can either be a negative or a positive. It's just a maximum value. Now, particles have a maximum energy at antinodes, and antinodes are half a wavelength apart on a standing wave. Now, antinodes are caused by the constructive interference between the two progressive waves which form your standing wave. Now, you've got to be able to be aware of the differences between progressive and stationary or standing waves. So here are the major differences between the two. In stationary or standing waves, the amplitude of vibration varies with position, yet for progressive waves, the amplitude of vibration is the same at every position. For a stationary wave, the nodes and antinodes do not move along the wave, they are fixed in position, whilst for progressive waves, crests and troughs move along the wave. For a stationary wave, between adjacent nodes, all the points vibrate in phase with each other, yet in progressive waves, the phase varies continuously along the wave. And finally, in a stationary wave, only resonant frequencies support stationary waves. So not all frequencies can produce a stationary wave, only resonant frequencies can do this. Whilst for progressive waves, all frequencies support progressive waves. So if we can summarize what we've learned in today's lesson, we should be aware of what a stationary wave is, an understanding of what nodes and antinodes are on strings, that the formation of a stationary wave by two waves of the same frequency traveling in opposite directions, and a graphical explanation of the formation of stationary waves will be expected, and you can also produce stationary waves formed on a string and stationary waves with microwaves and sound waves as well. So if we've been successful and we've learnt in today's lesson, we should be able to explain what is meant by a stationary wave, define the terms node and antinode, and describe the formation of a stationary wave by two waves of the same frequency travelling in opposite directions. So thank you very much for watching this video on standing waves, which is part of the waves topic in AQA A-Level Physics. Thank you very much for watching and have a lovely day.